Swayam Prabha. Digital India. Educated India.
Now we will move into joint probability mass function and joint probability density function of n-dimensional random variables or random vector of size n. Let me start with the joint probability mass function. Let me start with the two dimensional, that is easy. Let x1 comma x2 be a two dimensional discrete type random variables. That means x1 is a discrete type random variable as well as x2 is also discrete type random variable. With the CDF capital F of x1 comma x2. One can define the probability mass function in together, that is probability of x1 comma p of x1 comma x2, that is with the variable x1 comma x2, that means the probability of x1 takes a value small x1 and x2 takes a value small x2, where small x1 is the images of x1 or ranges of x1 and small x2 is the ranges of the random variable x2 or the images of x2. Put together, that is the probability of x1 takes a value small x1, x2 takes a value small x2. This is nothing but the P of collection of W such that x1 of W that is equal to x1 and x2 of W that is equal to x2 and W belonging to omega. That means this is an event, collection of possible outcomes satisfying this event. So, P of this event, that is a probability of an event satisfying this condition. So, this function is called the joint probability mass function of the random variable x1 comma x2. This is a probability mass at the point x1 and x2. You can go for a graphical representation of a joint probability mass function x1, x2. So, this is the probability mass function of x1 comma x2. That means at some point in the two dimensional plane x1, x2 plane, whatever the smaller heights, that is going to be the probability mass function at the point x1 comma x2. Both are discrete type random variable, therefore this can be represented in the three dimension plane. x1 is a one axis coordinate and x2 is another coordinate, and height z axis is a probability at the point x1 comma x2. The joint probability mass function satisfies two properties. This is always going to be lies between 0 to 1 for every x1 comma x2. The second condition, if you make a double summation of probability mass function at the different x1, x2, that is going to be 1. That means if you add all the heights over the x1 x2 plane, that addition is going to be 1. That means wherever there is a mass, it has greater than 0. If you add all the masses, that is going to be 1. From the joint probability mass function, one can get the probability mass function of x1 and x2. They are called marginal distributions. That means if I want to find out the probability mass function of x1 from the joint probability mass function of x2 by summing it over x2, I can get the probability mass function of x1. You can verify whether this is going to be a probability mass function. This summation value is always going to be greater than or equal to 0, lies between 0 to 1, and if you make a summation over xi, x1, that is going to be a double summation over x1 and x2, that is going to be 1. Therefore, this is a probability mass function of the random variable x1. Similarly, one can find the probability mass function of x2 by summing over x1 of joint probability mass function. So, this is a probability mass function of x2. The way we have done, we can go for n-dimensional random variable, then we can get the probability mass function of any one random variable by summing over the joint probability mass function of x1 to xn except jth variable xj. You can get the marginal from the joint distribution. From the joint probability mass function of n-dimensional, I can find the joint distribution of xi and xj by summing over x1 to xi minus 1, xi plus 1, xj minus 1, xj plus 1 till xn of joint probability mass function of x1 to xn. That means by n minus 2 summations without xi and xj, one can get the joint probability mass function of xi comma xj. That means always from n-dimensional random variable, either CDF or if they are discrete type random variable, you can get the lesser distributions of jointly by summing it over the other variables. So, by doing again and again, you can get the marginal distribution of one random variable. So, that means from n random variables, you can get the joint distribution of n minus 1, then n minus 2 and so on. Finally, you can get the marginal distribution of any one random variable. Let us go for one simple example how one can visualize the two-dimensional discrete type random variable as an example. Let E be a random experiment of EBA random experiment of tossing a unbiased coin three times. The random experiment is tossing a unbiased coin three times. Therefore, the omega is going to be the collection of all possible outcomes. That is, I use the notation H for getting head, T for tail. So, since we are tossing a unbiased coin three times, therefore, you will have a 2 power 3. So, you have 8 possibilities. So, head, 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 tail, head, or head, head, tail, and head, tail, tail, then tail, head, head, tail, head, tail, 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 H, then last tail, tail, tail. So, these are all the 8 possibilities or 8 possible outcomes of this random experiment of tossing a unbiased coin 3 times. Now, I am going to define 2 random variables in this random experiment, and our interest is to find out the joint distribution of these 2 random variables. First, let me define first random variable x as a number of heads in tossing a unbiased coin 3 times. The random variable y is nothing but a difference in absolute of number of heads and number of tails. You see it very carefully. The random variable x is number of heads, whereas the random variable y is difference in absolute of a number of heads and a number of tails. Therefore, you should know what are all the possible values of x, what are all the possible values of y. Then you can conclude what type of the random variable x and y. Then you can go for finding out the distribution based on whether it is a discrete or continuous. The way the x is defined number of heads and the random experiment is tossing a coin, unbiased coin 3 times. Therefore, there is a possibility you will get no times head or 1 times a head or 2 times a head or 3 times head. Therefore, the possible values of x, that is 0, 1 or 2 or 3. Whereas the y is a difference in absolute of number of heads and number of tails. Therefore, the possible values of y is going to be 1 and 3 because of a difference in absolute. Therefore, you can go for make out the table of different values of x comma y and what is the collection of possible outcomes which is going to give the values of x comma y. For example, suppose you go for x takes a value 1, y takes a value 1. That means number of heads is 1 and the difference in absolute with the number of heads and tails, that is also 1. That means the possible outcomes from the omega that is a head, tail, tail, or tail, head, tail, or tail, tail, head. All these three possibilities gives the value of x comma y is 1 comma 1. Okay. Similarly, you can go for what are all the possible outcomes in which gives the values 2 comma 1. That is going to be the number of heads is going to be 2 and the difference in absolute with the number of heads and tail, that is going to be 1. Therefore, it is going to be head, head, tail, head, tail, head, tail, head, head. The next one, you can go for finding 3 comma 1. If you go for 3 comma 1, you will get no possible outcomes. Similarly, if you go for 0 comma 1, there also you won't get any possible outcomes. If you go for 3 comma 3, number of heads is 3 and difference in absolute heads with the tail, that's also 3. That is possible with head, head, head. Similarly, you can go for 0 comma 3. Number of heads is 0 and the difference in absolute, that is going to be 3. That is possible with the tail, tail, tail. You see that there are totally 8 possible outcomes. So, one we have 3, other we have 3, and other you have 1 and 1. So, that total is going to be 8. Therefore, now we can go for finding out the joint probability mass function of x comma y using this box. That is when x takes a value, when x takes a value 0, 1, 2 or 3 and y takes a value 1 or 3, we can make a table. X takes a value 0, y takes a value 1, that is nothing, therefore the probability is 0. When x takes a value 1, y takes a value 1, that is 3 possibilities. It's an unbiased coin, therefore the probability is going to be 3 by 8. When x takes a value 2 and y takes a value 1, there are 3 possibilities, therefore this is going to be 3 by 8. When x takes a value 3, y takes a value 1, nothing, therefore no possible outcomes, therefore empty set, probability of empty set is 0. Similarly, 0 to 0 comma 3, that only one possibility, so 1 by 8. 1 comma 3, there is no possibility, therefore it's 0. And 2 comma 3, there is no possibility, therefore that's also 0. And 3 comma 3, there is only one possibility, therefore 1 by 8. If you add all the values, 3 by 8 plus 3 by 8 plus 1 by 8 plus 1 by 8, that is going to be 1. If you make a row sum or column sum, you will get the marginal distribution, and if you add those values, again you will get the 1. So it's 0 plus 1 by 8, 1 by 8, 3 by 8, 3 by 8, 1 by 8. If you add all these values, it's going to be 1. Similarly, if you add 3 by 8 plus 3 by 8, that is 6 by 8, 1 by 8 plus 0 plus 1 by 8, that is 2 by 8. So if you add 6 by 8 plus 2 by 8, you are getting 1. That means the probability mass function of x takes a value small x, that is going to be for different values of x, it is 0, 1, 2 and 3. So it is going to be for x takes a value 0, that is 1 by 8, for 1, 3 by 8, for 2, 3 by 8 and 3 1 by 8. So this is going to be a probability mass function of x. Similarly, one can make a probability mass function of y. So different values of y is going to be 1 and 3. So for 1 it is 6 by 8, for 3 it is 2 by 8. So this is a marginal distribution of y. So from this page one can get the joint probability mass function of x comma y. From the joint distribution you can always get the marginal distribution of x and y separately, or you can find out the marginal distribution from the random variable x itself. You don't need finding the joint distribution then find the marginal of x. You can find the way we have defined x, you can directly get the probability mass function of x. But here what I am saying is, if you know the joint distribution you can always get the marginal distribution. The other way or the converse is not true. That means from the marginal one cannot get the joint always, whereas from the joint distribution you can always get the marginal. Therefore here we get the probability mass function of x and y from the joint probability mass function of x comma y. This is the easiest example. Since both the random variables are of the discrete type, we are able to give the joint probability mass function of the random variable x comma y. So with this example, let me complete the joint probability mass function. In the next class, we will go for when both the random variables are of the continuous type, then one can define the joint probability density function. That we will do it in the next class.